Okay, so we will try to do this question also, 22nd question. Uh, so actually you can remember that this is new type of question, okay, because we have to find the inverse Fourier transform. I think you can remember that we didn't pay much attention to find inverse Fourier transform, no? In case of continuous time also. But here I put this question, okay. But if you know the concept, it is okay. You can easily find the inverse Fourier transform, okay. So we will try to find that one, okay. So here we have the frequency domain signal. So we have to find the inverse Fourier transform. So we should have a frequency domain signal, and that frequency domain signal, we have to find the time domain signal. No? We have to convert to a time domain signal using inverse Fourier transform. So this is discrete time inverse Fourier transform. Okay, so we know the identity, already know the identity. So if you have inverse Fourier transform of frequency domain signal, okay, you will have time domain sequence. Okay, so the identity is, so this omega is a continuous time variable. We can't guarantee that it is a, discrete time variable. Although this n is discrete time, we can't guarantee this omega is discrete time. Most probably it is a continuous time signal, a continuous time variable. Okay, so we will use the inverse Fourier transform identity to find the inverse Fourier transform of this this time, frequency domain signal. Okay, so you have we have to integrate with 2 5, you can remember, I think. So here we have our frequency domain signal and e to the power j omega n d omega. So this is the inverse Fourier transform identity. Okay, so we can use this directly now to find the inverse Fourier transform. Okay, so we have this x omega. So I will get Fourier transform, inverse Fourier transform of this x omega, capital X omega. So definitely I will have a time domain sequence, simple xn, let's say it is simple xn. So we have this integration 1 by 2 5 within 2 5. Okay, so here x omega is 2 5 delta omega minus omega naught, 2 5 delta omega minus omega naught e to the power, sorry, plus j omega n dy. So this is the identity. Okay, so I think we can do the integration very easily. Okay, so here you can see that this 2 5 and this 2 5 will cancel out, and you will get only this delta function omega minus omega naught e to the power j omega n d omega. So you can see that we are going to integrate this expression with respect to omega, capital omega. So this capital omega is the independent variable. Okay, so this capital omega is the independent variable. Okay, and this n also independent variable. Okay, it is a variable, but this time, because we are going to evaluate this integration with respect to omega, so we can keep this n as a constant. Okay, so this time this we can keep this n as a constant. Okay, so we have to do the integration. So I think you can remember we have many time use a property with regards to this impulse function. Okay, so you can see that this is unit impulse function. No, this is unit impulse function, and it is actually shifted unit impulse function. No, it is shifted unit impulse function. Okay, and you can see that this omega is a continuous variable. No, this omega is a continuous variable, not discrete variable. Okay, so this is continuous variable. This omega is a continuous variable. So this is continuous time, okay, shifted unit impulse function. No, shifted unit impulse function. So I hope you can remember one property here. Okay, so with respect to continuous time unit impulse function, we learned few properties. No, actually we have learned two properties, very important properties, and we have used that two properties many times to solve some question. Okay, so here also we have to use that properties. Okay, so let me take the property. Okay, so here so this is unit impulse function. No, unit impulse function, continuous time unit impulse function. So you can see that, yeah, this one. So this is one property. No, I think you can remember this is one property. Actually, this is a definition. No, this is a definition. One definition of unit impulse function. Okay, we have discussed many times about this property. So I'm not going to explain it here again because it will be boring to you. Okay, so this one also another property. No, most probably we have used these two properties. I think you can remember for many Fourier transform, Fourier analysis problems. Okay, we have used these two properties. Okay, and these are the actually definition. Okay, these are definition of the unit impulse function, and there is this property also. Okay, so this is with respect to unit impulse function, shifted unit impulse function. So here we have to use this definition actually. Okay, so you should remember these three definitions definitely. Okay, because this definition are very important. Okay, so you have to use this definition many times. Okay, so I will write it with respect to actually three definition. We have learned these three definition previously also, but these two already we have used in many times. Okay, this used in many times. Okay, but this property I think we didn't use, but we have discussed about this property. Okay, so these are the property. So if you integrate within very small function, this delta t with dt, you will get 1. This is one definition of delta t function. And another one is if you integrate minus infinity to plus infinity, delta t with another time domain signal phi t, any arbitrary signal. Okay, so this is any arbitrary signal. So you will have phi 0. Okay, so we have used this property also to solve many questions. Okay, that means here we have unit impulse function like this, and any arbitrary time domain signal phi t. Okay, so if you integrate this multiplication, that means here you will get some value. Okay, and if you integrate this from minus infinity to plus infinity, you will get here phi 0. Okay, value. Okay, I think we have used this property many times. So I'm not going to explain it anymore. Okay. And the third property, we can say that third definition actually. Okay. So third property is minus infinity to plus infinity, 5t, any time domain signal, multiplied with delayed unit impulse function. Okay, shifted unit impulse function with respect to dt, you will get 5t naught. Okay, so this is another important property. Okay, so here it is the idea is like this. So if you have shifted impulse at t naught, okay, so this is time, and if you have arbitrary signal 5t, okay, if you have arbitrary signal 5t, so this cross point, okay, if you integrate this minus infinity to plus infinity, you will get here 5t naught. Okay, so this cross point will be 5t naught, and if you integrate it minus infinity to plus infinity, you will get this result. Okay, so we are going to use this property this time. Okay, I hope previously we didn't use this property, but we have discussed. Okay, these three, all these three properties we have discussed. So I think you can remember these things. Okay, anyway, we will use. Okay, so you can see that here we have frequency domain, but it is continuous time. Okay, so as xn, we have within 2,5, this integration within 2,5, we have delta omega minus omega naught e to the power j omega n d omega. Okay, so you can see that this is not time domain signal, this is the frequency domain, but this time and frequency is identical. No? The same value you can get for time and frequency. So there is no any difference. So signal, this signal, you can write like this within 2,5. Instead of this omega, I will put t here. Okay, it is all right. I just change the letter of this independent variable. Okay, omega. So this is a continuous time variable. I just change the letter to t. Okay, so here we have t omega naught e to the power j, here omega t n omega dt. Okay, so here I get t as omega. Okay, so I have dt is equal to d omega, so I have just put. Okay, so you can see that I get this kind of function. Okay, this kind of identity. So it is very similar to 5. Okay, delta t minus t naught 5t. Okay, so here 5t is ejtn. So this is 5t. Okay, so you can see that this is a time domain signal, t domain signal. Okay, okay, so instead of this t, we have to put this omega naught. Okay, so we have ej omega naught n. Okay, so this is the answer. No? Okay, so xn is nothing but e j omega naught 10. Okay, so this is the xn. So you can see that we have found, we have xn, and if we get the Fourier transform, we have x omega. Okay, we know x omega, that is 2,5 delta omega 2,5 omega minus omega naught, and here we have e to the power j omega naught 10. So this is frequency, and this is n time domain signal, and this is frequency domain signal. Okay, so this is Fourier transform, and this way it is inverse Fourier transform. Okay, so this identity is already proved. No, so we asked to prove that identity. So you can see that it is already proved. Okay. So you have to use this property. Okay. You have to use this property with regards to shifted unit impulse function, continuous time shifted unit impulse function. Okay. So I hope you got that. Okay. So we will try to do another question. Okay. Also. So if we have this kind of function, okay, this kind of function, okay. Now I will do, yeah, I will do this xn cos omega naught n, okay. So I'm going to do this one also for you, okay. So we have this function and we have to find the inverse Fourier transform, no? Sorry, Fourier transform. So we have xn time domain signal and we have to find the frequency domain signal x omega. Okay. So so if we use the identity, okay, so you can use that identity also, that Fourier transform identity, okay. But here n is not defined. So n can be goes minus infinity to plus infinity, okay. But it is discrete value, okay. It is a discrete value, okay. So so I think if you use that identity, okay, that Fourier transform identity, you will get minus infinity to plus infinity. Xn is cos omega naught n, okay, and e to the power j omega n, okay. So minus j omega n. So here you can find omega also, no issue, okay. So this is the identity you will get, okay. Okay, then you have to apply some n value and uh, find the Fourier terms, okay, Fourier terms, okay. But you can see that many terms you will get, okay, and you have to you have infinite number of terms. So sometime in using mathematics, we can reduce these terms up to some finite number of terms, okay. So actually this kind of function have a convergent value, okay. So we will have some finite number of terms, but to get that finite number of terms, it is somewhat hard to do the calculation, okay. So simplification is somewhat hard. We have to use different substitution and we have to do mathematical work, okay. So so what about if we can use this property, this fact? What about if you can use this fact? Okay. So here you have e to the power j omega naught n, that is time domain signal, have 2 5 delta omega minus omega naught. Okay. So I think same result you will get for continuous time case. No, if you can remember, you maybe remember that same type of question, same type of identity we have for continuous time case also, okay. So this actually you can use this identity, okay. So you can use this as a known fact and you can use this knowledge to find this type of question, okay. This type of function Fourier transform, discrete time Fourier transform. So you already know that using Euler formula, we can write this cos terms in with respect to with respect to uh, exponential terms. So I will directly write it without doing much calculation. Okay. So here you have half e to the power j omega naught n plus half e to the power minus j omega naught n. Okay. So cos omega xn, this is the xn cos omega naught n. Okay. So if you get the Fourier transform of this xn, that means you have to get the Fourier transform of these two function. Okay. So using the linearity property, you can say that there is a addition of two function. So you can get separate Fourier transform of e to the power j omega n plus f of e to the power minus j omega n, like this. Okay. So you can get this Fourier transform and Fourier transform. Okay. So this is linear and you can get this half out of this Fourier transform operation. So you will have to Fourier transform, no? Fourier transform of e to the power j omega n, Fourier transform of e to the power minus j omega naught n. So you can use this property, this identity, and you can find. No? So here you have e to the power j omega naught n, e to the power j omega naught n, 2 5 delta omega minus omega naught. No? So you have 2 5 delta omega minus omega naught. So you have this function. So this omega is, so normally we use this omega as capital omega. No? If it is simple omega and capital omega, it is okay. In case of continuous time, we use simple omega, and in case of discrete time, we are using capital omega. So you can use capital omega here. So omega minus omega naught, because this is omega naught plus, and half is there. So 2 5 half, okay, delta omega. So here you have minus omega naught. So here you have minus omega naught. Okay, that means you have delta omega plus omega naught. Okay, omega plus omega naught. So very easily you can find the Fourier transform. Okay, using that identity. Okay, so I hope this kind of question also you can find the Fourier transform very easily. Okay, what you have to do that you can write these sine terms and cos terms in terms of exponential terms. Okay, using Euler formula. Then if you can find the Fourier transform of different exponential terms using that identity, this identity, okay, this identity, you can easily find the Fourier transform. Okay, so we will do this question also because it is, we can do it easily. It will not get much time. Okay, so definitely this type of question will come to your exam. So you have to, you should be able to do this kind of question. Okay, so I am writing this sine terms and cos terms with exponential term directly without doing much explanation. Okay. So here sine to n, I can write it as half e to the power j to n, correct? Minus half e to the power minus j to n plus half e, this cos term, now sine term is finished, this is sine term, and cos term I can write e to the power j for n plus half e to the power j minus 4n, like this. Okay, so uh, so find in the Fourier transform of this f means find in the Fourier transform of all these terms. Okay. So using linearity property, you can find separate Fourier transform of this exponential term. Okay, jn plus half f Fourier transform of minus j 2n half Fourier transform of the j4n, okay, plus half Fourier transform of e minus j4n. Okay, so you can write, okay, like this. So using that identity, we have that identity. Okay, we will get it here. So try to remember this identity. It is very useful. Okay, it is very useful actually. Okay, so you can see that here e to the power j omega naught n. So this is omega naught, no? This is omega naught definitely. So you have here half 2 5 delta capital omega minus 2 plus half 2 5. Here it is minus j2. Okay, so omega naught is minus 2. So you have omega plus 2, omega plus 2 plus half 2 5 e to the power here 4. This is omega naught 4. With respect to this term, omega naught is 4. Okay, so you have 2 5e 2 5 delta here delta. Okay, delta omega naught, omega minus omega naught is 4 here, plus half 2 5 delta. Here omega naught is minus 4. That means omega minus minus 4, that means plus 4. Okay. So this is the answer, no? So easily you can find. Okay. So I hope this kind of Fourier transform now you can find. Okay. So I hope you can get the idea. Okay. So if you have any problem, you can call me or email me. Okay, then I can help you. Anyway, you should go all this question before the exam. Okay, then you will get sufficient knowledge to face the exam. Okay, so no need to do any past paper or other things. Okay, just focus on this tutorial. Okay, then the all important point are there. We have covered are there. Okay, so I hope you get it, you got it.